33. They want us to approximate the cube root of 1001. So let's analyze this, because that's what I have to use. So this is what this part is saying. The function applied to x plus a little bit of error. This is the error, the differential of x. So I need to identify the function, I need to identify x, and I need to identify the little error before I even look at anything else. Can anyone, by looking at this, give us a function that you see here, give us an x that you see here, and a tiny error that you see here? You can say, do I see any, all these three here? Yes, we do. So can anyone give us a function?
Cube root of x.
Of course. Can anyone look at this number and say, oh, I know, x is this and tiny error is that? Also keeping in mind that this is the cube root, of course.
X is 1000 and the error is 1.
That's it. What if I had 999? What would have been x?
1000.
And what would have been dx?
1.
Careful.
-1.
-1. Exactly. Awesome. Good. So for now, we identified this piece. So I can write the formula. So I can put this page away. F of x plus f prime of x dx. The problem is solved. You can say, how come? Well, all these depend on what I just determined. So once I determine the function x and dx, all I have to do is just plug them in. This will be 1. This will be the function evaluated at 1000. And this will be the derivative evaluated at 1000. So it's done. This is the 99% of the problem. Identifying, by looking at this, identifying the function x and dx. So then, let's change the function into x to 1/3 so we can find its derivative. Can anyone give us the derivative?
One-third x to the -2/3.
Excellent. Or 1/3, the cube root of x squared. Done. The whole thing is done. So I'll copy f of x plus dx, which is the cube root of 1001. I'll put the squiggling because they're not equal. Can anyone tell us what is f of x? The cube root of 1000. Let's write it. The cube root of 1000, and then plus, yes, and then plus 1/3 the cube root of 1000 squared times dx that you told me is 1. That's it. So you told me that this was 10. So this is 10 twice, right? The cube root of 1000 times the cube root of 1000. So it's 100 times 3. So plus 1/300, which is 3001 over 300. You had no idea that you could determine the cube root of 1001 with a linear function. You can say, yeah, but this is not exact. True. Why it's not exact? Because I used dy. So now you should always do this. Go in here, clear, and say, okay, 1001 to power 1/3 and 3001 divided by 300. Isn't calculus great? That's all there is to it. Once I identify the function x and dx, I only have to use the formula, and it's done. I like to look at a word problem. Let's take a look at 42, unless you want to choose something else. 42. The radius of a circular disk, is given as 24 centimeters with a maximum error in measurement of 0.2 centimeters. Use differentials to estimate the maximum error in the calculated area of the disk. So the radius is this, the error is this. Use differentials to estimate the maximum error in the calculated area of the disk. So let's talk about this. As you know, every time we look at the word problem, we have to dissect everything. What is this? What is the 24?
Is that the function?
Careful.
X?
It's x. It's x indeed. You can call it r if you want to call it radius. That's the x. What is this? If this is x, what is this?
Dx?
Of course, it is dx. So I identify the x and identify the dx. What do I need to identify next to be on the right track?
F of x?
Exactly. Now let's think for a moment. What am I asked to find? The error in the area. So what is the area of the disk equal to? Pi x squared. So I have x, I have dx, I have the area. What are we asked to find? Not the exact, so I am not asked to find dA. What will dA be? dA will be the area with 24 plus or minus 2.2 minus the area with 24. But no, they don't want the exact. They want us to find the approximate delta A. What is the notation and how does the approximate error looks like? What should I write for the approximate? If it's not delta A, what could it be? What is the other one?
dA?
dA. Good. Can anyone give us the formula for dA? Instead of dy, I have dA. So what should I write?
F prime of x times
A prime, very good, of x times,
Dx?
that's it. That's what dA is. That's why we wrote this first. So if I have here dA, then this is A prime of x times dx. If I have w, then I have w. If I have t, then I have t. Excellent. Good. Can anyone differentiate this function? This is a function of one variable. X is, we're not talking about related rates here or anything like that. Just differentiate this. And whatever you give me, I'll say dx.
The 2 pi x.
That's it. All I have to do now is plug in the numbers. That's it. 2 pi are numbers, x is 24, dx is 0.2. And that is what? The approximate error in the area created by this, not the exact. This will be the exact. So if there is an error in the radius of 0.2, that will trigger an error in the area. This is what we had at the beginning. Where is it? The change of 0.2 in x, or the radius, triggers this change in the area. Of course, it's tiny, but I'm showing it what it is. This approximate change. If you want to determine the exact change, you have to calculate delta A. But if you're happy with dA, then this is what you will determine. This is triggered by 0.2, and we'll see how much this is. The approximate one, not the exact. This will be the exact. Okay, so where am I? Page 8. So dA equals 2 pi 24 times 0.2. And in a minute, I will ask you about the measurement unit. So 2 pi times 24 times 0.2, give me the number, 30.16. Measurement unit. This is the actual, this is not a rate of change. You cannot give me 2 measurement units. So this is the approximate change in the area of the disk if the radius has an error of 0.2 centimeters. What will this be? What is the measurement unit for 30.16?
Centimeters?
Area.
Centimeters squared.
Excellent. Centimeters squared. Great job. Any questions before we look at part B? Because I think there is a part B there. What is the relative error and the percentage error? Fine. So let's talk about part B. So sorry about that. Let me write part A here. Then part B. A relative error and then percentage error. Okay, by relative error, we mean error over exact, over original. And this will be just the percent, changing the relative error into percent. You'll see in a moment. So the error is dA. The original is A. This is the relative error. dA is 2 pi x dx. 2 pi x dx. A is pi x squared. Simplify, 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 simplify. Twice dx over x. Twice 0.2 over 24. No measurement unit. No How come? Centimeter squared over centimeter squared, no measurement unit. So I'll simplify, and I have 12 divided by 0.2 divided by 12. 0.2 divided by 12. And I got 0.016667. No measurement unit. It's centimeter squared divided by centimeter squared. And now the percentage error. Can anyone change this into percent for us?
1.67%.
That's it. So what does this mean? It means that the error, if you cross multiply, the approximate error is 1.67% of the area. Cross multiply. So you can write dA over A equals 1.67%. Cross multiply. dA equals 1.67% of the actual area. Okay, the last topic that I wanted to discuss is the linear approximation. So we will go back to the same graph, but I have to graph another one. Same thing, same function. So now this time we're going to say that this is A. We're going to say that this is f of A. This is again the same point P. Yes, of course, I'm going to draw the tangent again. I know you got used to it. I know you're going to say that the slope of this tangent is what is the slope of this tangent?
F prime of A.
Thank you very much. And we do have a point. Point P is A comma f of A. We have everything we need to determine the equation of the tangent. So can anyone give us the equation of tangent at P? How do I write it? I have a point and I have the slope. Y minus y1 equals the slope times x minus x1, where x1 is A, y1 is f of A, and the slope is f prime of A. So then y minus f of A equals the slope times x minus A, and of course I'll add f of A to both sides. This is also denoted by uppercase L of x, and it means the linearization of f of x near, or at if you want, A. So what am I saying with this? I'm saying that if you need to approximate the function very close to A, you will not encounter a huge error if you evaluate the equation of the line at that value. Okay, so this is also called, so this is f of x, approximately f of A plus f prime of A times x minus A, because this is our function, not the linear function, right? Our function can be approximated, so this is the approximation, the linear approximation of f of x near or at A. That's it. And this is the end of the chapter. Now we have to practice this. So, what is the concept that we're just looking at? This concept says this.